This is a supplementary lecture to the Executive Black Belt, Executive Green Belt class, and we are going to be covering hypothesis testing in this lecture. This lecture covers slides 109 through about 143 in your text. So what I want to do in this lecture is give you a little bit of a background of hypothesis testing, organize it a little bit, and organization. And then we will simply do examples, and that's it. And the examples will be from files that you have in the book. We'll be doing them both. Each example we'll be trying to do in Minitab, so you have that, and also in Excel statistics. So you'll be able to find out, statistics, see if I can spell. There we go. All right, in Excel statistics also. So you'll get both sides of it. You'll get to see it twice, and you'll get to see what are the key takeaways. Okay? Also, I want to point out that hypothesis testing always goes along with another technique called confidence intervals, and so we'll get both at once. It's kind of like the old search commercials where you get 2 mints in one. Okay. Hypothesis testing is a pretty broad subject, but here are the cases that we're going to cover. We're going to cover testing of means. We're going to cover testing of variances, but I'm going to make that a little bit more specific, and we'll just say standard deviations. We'll convert it to that. We're going to talk about proportions. And remember, a proportion is just sort of the pure form of a percent, right? When we say 25%, that just means the proportion is 0.25, okay? Proportion is always sort of pure of any sort of multiplicative factor. But that's really what we're talking about. And finally, we'll round it up with a very brief discussion of testing medians, and we'll do that. So just to give you, here's the symbol that we'll be using for each of them. Here's the test or tests that we'll use. So the symbol that we use for testing means, we'll be comparing, say, mean mu with mean 2, with mean 2, which would be mu 1 and mu 2. So that's what we're testing. We're going to look at the t-tests. Okay, we'll look at 1 sample and also 2 sample. We'll look at both of them. We'll be testing standard deviations. Those are sigmas. Okay, and we'll be looking at something called the f-test. We'll also be looking at something called Levene's test. Okay, and we'll tell you what the distinctions of why would you use one over the other, which is a little more complex perhaps than 1 and 2 sample 2. When we talk about proportions, we'll be talking about the pies. Okay, and here this is very simple. We'll be talking about 2 proportion test. And for medians, we're talking about news. And there's lots of different tests for medians. They basically all work more or less the same. We're going to be looking at Kruskal, Wallace, and I don't know if they all have 2 associated with them. Many median testing tests actually have 2 names. In Excel stats, we'll look at the Mann-Whitney test. Okay, so those are the ones that we're going to be looking at, and let's go to it. By far, I think I said this before, the most important ones, the ones that you want to star, are the first 3, particularly the first one, and sort of like the decreasing stars are kind of telling you sort of how useful these things are. By far the one that you're going to be most interested in is the test of means. Those are t-tests. Okay, so we'll do a couple of examples in there. So let's get to it. The first example that we'll do is one that is, oh yes, what we'll want to also do is keep in mind, before I go into this, the setting that's most common is going to be when we have a y that's a num, let's put it this way, num, and a x that's a cat, right? Where this one right now is only going to have two categories. So for example, we might have driver gas mileage by gender. Gender only has two categories, male, female, so that would work for this section. When we want to do more than two categories, like say eye color, you maybe want to measure, if you're an optometrist, maybe pupil dilation from a certain type of chemical solution, and you want to measure that by eye color. You could have blue, green, hazel, brown. More than two categories, that'll be something called ANOVA. All right, but to start out, this is what we're going to come out with. If we have a y that's a number and x that's two categories, first we'll talk about means. Okay, that's a case where we'll want to do a t-test. Okay, and we'll talk about the t-tests are for means. But also with this type of x and y situation, num-cat, we'll also be talking about variances, and that's the f-test and Levene's test. And again, we'll tell you what the distinction is there. So those are the first ones that we're going to cover. We'll cover means first. So let's get to it. Let's take the first example, which is not quite a y and an x. It's just going to be one y. But you'll see, I think, the relation here. And in this case, we're going to be doing a file called, this is the example on page 118 in your book, and we'll be using the file driver speed. So in this example, what we're doing is maybe a benchmarking study, and you can imagine that you work for the state police or something like that, and you wanted to clock a bunch of people who were driving on Route I-95 and calculate their speed. So we looked at the driver speed, and the question that might arise is, let's compare the speeds that we're clocking to the speed, to some speed that would be some sort of standard, say 55 miles an hour. Let's suppose it was a stretch of highway that was heavily populated. So what we want to calculate is driver speed. I'll call that DS. That's definitely a num. And we'll use a t-test to compare whether or not the driver speeds on average are above or below 55, but we'll do it in a way that will say whether that will determine whether it's statistically significant or not. Remember, that's what hypothesis testing is about. So if we were doing our PGA wheel, remember the old PGA wheel, the first question would be, I wonder if average speeds are above 55. Let's make a plot of it first, and then let's run a test. Okay, we're going to be most interested in this, but just for grins, let's go ahead and do the whole 9 yards, and we'll do it in Excel stats. So in this case, we've got one num, right? We only have one num, so let's go ahead and do that in Excel stats, and we'll get the test along for the ride. Then I'll show you how to do it in Unitest. Okay, in Excel stats, the first thing that we need to do is get the data file open, which I've got right here, driver speed. Here it is. Select it. One num. Okay, so the first thing that we ought to maybe look at is some sort of comparison to see whether we think it's above, on average, above or below 55. A nice way to do that, or an easy way to do that, is to look at the histogram. And remember, I like to give a little bit of room on each side, so we'll go between, say, 45 and 85, maybe 40 and 85. And we'll put a few more classes in there. So if we look at this, just taking a look at the histogram, the histogram isn't the only tool, but look at all, if we look at, I'm going to try and highlight or color, color these. Look at all these boxes. All of this are drivers that were above 55. boy, it sure looks like there's more drivers that are more 55 than less. And in fact, if we look at the average speed in our data set, it's 64, which is clearly above 55. The question is, do we have enough statistical evidence to conclude that it really is greater than 55, and if we went out on a different and got a different sample, that it would be below? Let's check it out. For that, that's a hypothesis test. So we're going to write it out. We're going to write out the hypothesis test. So let's go ahead and write that. All right, so let's write out our null. Our null is always going to be there. I don't see any evidence for what I want to make. So the first one would be maybe mu is that the actual mean is less than 55. Oops, let me just say is equal to 55. Let's just try that. Is equal to 55. So mu is equal to 55 versus, in this case, our alternative, we really want to see that we really want to test that if it's greater than 55, right? So it sure looks like, and that's what our graph said, sure looks like that's the case, looks it. Like I said, there's other graphs that we'll be able to use to tell that as well. So that's what we want to test. Okay, and remember what we're going to be doing is we're going to be running this test, and then we'll look at the p-value. So let's see how we do that in Excel Stats. It's actually quite straightforward. All right, so here we are in Excel Stats. The quick way to do it is to actually go and look at the mean plot and to see if that overlaps 55 when we put in the 95% confidence interval. It doesn't. That's one tip-off that we're going to get a significant p-value. But let's do it for real. Let's run the test. The test is found on the tab Tests. Okay? It really is almost, it's all basically done for you. Once you get the data in there, you just have to know where to look. And here it is right here. Now, the one thing that we do need to do is we need to make sure that we test the right mean. So we'll put in 55 there. And then I get the right alternative. So I'm not looking at whether it's less than 55. I'm looking at whether it's greater than 55. And that should be a 55 there. Whoops, let's see. Let me go a little bit higher just to make sure that we've got it right. Well, I'm going to shut this down actually because I think I did get it a little bit wrong. I do this once in a while where I hit the wrong, I go to the wrong place. There it is right there. That's what we want to test. We want to test the mean of whether it's 55 versus it's not 55. See, I typed in the wrong thing first last time. I've got my data in there. And remember, we've got to click the right one, and there it is, a p-value that's very low, right? It's 1.1, but there's 5 zeros in front of that 1.1. Okay, so that's important, and so that's going to lead us to say we reject the null because p is low. Remember the phrase: if p is low, the null must go. But also, we can also see that the confidence interval does not overlap 55. In fact, it's all above that. So all of those roads kind of lead to Rome. It's in fact 60 to 68. So we'll take a look at, kind of draw that up. We certainly have a p-value equals 0.00011, which is certainly less than 0.05. Which means reject the null, reject H0. And that also means, remember when we looked at the confidence interval, the true average was somewhere between 60 and 68. And if we put the point for 55, we notice that it's outside of that interval. And if it's outside of that interval, that means that that would be a bad estimate to estimate that it's 55. That's another indication that this is significant. So we will reject the null and make a conclusion that indeed people are driving above 55 on average in this on this particular stretch of road. Now the question is, now let's convert it back to real language, practical language. What does this mean? Well, if you're the police department, maybe you put up some extra radar guns, maybe you ignore it, maybe you find out if it's at other times, etc. Okay, but there's some action, and now it's justified because you found that statistically that's true. So that's an example of the one sample mean. Let me show you how to do that in Minitab. It's a little bit different in Minitab. Okay, so in Minitab, the first thing we're going to do is we're going to get the data into Minitab from Excel. There it is, okay. We can do the graphs as well, but let's go and do the statistics, or the t-test. This is a one sample t. Now notice you didn't need to know that in Excel stats. You didn't need to know it was a one sample t. You just did the means test. In Minitab, you need to know it's a one sample t. So we have one sample, so we're going to be doing the one sample t, testing means here. We have samples in the column, so I will select the speed. And I want to perform the hypothesis test. My hypothesized mean is 55. I can ask Minitab to make a box plot if I want. I like that box plot. You'll see that this is kind of it's not the most earth-shattering thing, but it's an interesting plot. Let's go to the options. Now, here's where we can actually, in Minitab, we can change the alternatives. In this case, we want the alternative greater than. We want to test to see whether it's equal to 55 versus it's greater than 55. You know, if we left it at not equal, that would have been just fine. We could have used the confidence interval to tell us where to find this. It turns out, though, that your test is just a little bit more powerful if you know where to look. So no harm, no foul if you just used it as a not equal. Let's let it rip. And when we let it rip, we see, indeed, there's our 55. There's our confidence interval. You see that? Actually, it's just a confidence bound, but it's that's how we do it if we only have one-sided. It's called the confidence bound. And there you see, there's our estimate. It says that it's a little bit greater than, say, 62. And there's our 55. So clearly, this is going to reject that null. And let's check it out. Yep, there it is. Look, the p-value, Minitab doesn't give you as many zeros. It just says, nope, it's equal to 0 if it's less than, say, 1 in 10,000. But there you go. Okay, so again, Minitab gives a 95% bound as opposed to the p-value. Now, just to give you an idea, I'm going to use a control. If you use Control-E in Minitab, you can get back to where you were. Let's put in, instead of the greater than, let's just put in the not equal and see what the difference is. The only real difference is it now has an interval. You see it starts and it ends, whereas before it just gave you a bound. But we'll see that the price that we pay for that is that we moved a little bit to the left. And there it is right there. See, we went from like 61 to 60. We lost a little power in that test. But certainly this test was powerful enough to make that decision above 55. Most people find this to be more easily interpretable, that confidence interval rather than confidence bound. Okay. And that's also reflected here. Notice it's giving the same answer. See that? It's the same answer. Okay. So let's do another example here. Let's move on to the example that's given on 122 in your text, and I'm going to shut down Excel statistics or the driver speed. And let's do the example. I'll shut down some of this stuff too. One of the things that you have to always look out for is that there's lots of things that end up getting open and all that. So I advise you, when you make conclusions from things, to pop them into a PowerPoint or pop them into some logbook that you have when you make certain conclusions from analysis. For this example, we are going to be looking at, this is now a 2-sample T, and the difference is, you'll see in just a moment, is when you draw the box, you'll have something on the left-hand side, and it'll force you to make a comparison between some data and another group of a different data, as opposed to last time where we made comparison of data, of the mean of data to a number, right, 55 miles per hour. It's a little bit different. So what we're going to look at is we're going to look at, I can put this up, sorry. We're going to look at backlogs before and after. where we are over there. Okay. So let's look at backlogs before and after. And here what we've got is we've got a, and let me just do it right here in the, let's just do this whole thing right here in the file. We have got a, let me draw the box here. We're looking at backlogs. Could be anything, right? But in this case, it was backlogs for a healthcare company in terms of their paying claims, and that's a bad thing, right? So we'd like those backlogs to go down. And it was a count. You can see it's a number. That's a numerical variable. And what they wanted to look at was before and after they made a process change. Okay, so that's a cat, right? Before versus after. So we've got a cat here and a number here. All right, we draw our PGA wheel, and you'll see it's one num, one cat. First thing we ought to do, this is, I wonder if our change has worked. So the first thing we do is make a graph, then maybe do some analysis, then maybe make a conclusion. Okay, let's make a graph first. If we're in Excel statistics, we're talking about one num, one cat. So let's get that done. I'm going to show you how to do this, and in this case I'm going to use the box plot, and we're going to show you how to read the box plot. Okay, well this is pretty good. You can see this pretty well. Whoops, now we can't. There we go. Okay, so to see if the means are different for a box plot, here's a box plot, and just to give you an idea, with a box plot on the left-hand side here is our output, and this will be our time period, right, before versus after. So that's partly how you read a box plot. What we're going to be looking for is we're going to be looking for the difference between where the hovering is of the two boxes. If one box is sort of hovering above another, we might ask the question, I wonder if the means are different. Okay, so that's how we look at a box plot. If they hover at about the same area, if the boxes are more or less aligned, their centers are more or less aligned, we're probably not going to ask that question all that deeply. Okay? I do what I call the UFO test. I pretend that these are UFOs, and if one is sort of hovering above the ground, in other words, just taking off, and the other is still stuck on the ground or something like that, I might say, aha, I think that there's a difference in these UFOs. I think there's a difference in means. For that, we'll do a two-sample T. Let's go ahead and do that now in, Let me mark it in. It looks like the means look different from the box plot. Okay, so let's check it out. Let's see if it's true. We're going to do a two-sample T. Get rid of some of this stuff. There we go. So select this, Excel statistics, one num, one cat. We already had it, I guess. I didn't have to do it again. And we'll go to tests of two categories. You'll see later we'll be able to go to test of n categories, but let's just do test of two categories. In this case, we just want to see whether they're different, so let's leave it at that. There's my hypothesis test. You see there it is right there, two sample t tests, and before versus after. And we've already got the not equal alternative. And again, look at this p-value, very, very small, 2.99 times 10 to the minus 25. In this case, there's 25 zeros in front of that. That's pretty small. You can see the confidence interval does not overlap 0. So no, and it's not even close. So no way does it, is this going to, this is absolutely statistically significant. So let's write out the whole thing, which I neglected to write out the test. But let's write it. Okay, our H0 would have been mu before is equal to mu after. versus HA, mu before is not equal to mu after. Okay, we got a p-value was certainly, absolutely, 100% less than 0.05, much less, right? Which means that we reject the null in favor of the alternative. They're definitely different. Okay, they're definitely different. If you want to know sort of how much it improved or how much it changed, the confidence interval, and when we looked at the confidence interval, we found that that confidence interval was 34 to 41. So that would be our estimate for how much it changed. Okay, point estimate of 37.7, but a plus or minus amount such that you get an interval of 34 to 41. Okay, let's do one more because this is so key. Let's do one more. Let's do software usage. Now this one is not in the book, but is, I think you'll see it right away. I think you'll see the value of this. And incidentally, we're going to see the value of this box and whisker plot in this one as well. So if we look at software adoption, here we've got a lot of variables, you see. Let's do adoption, clear this. In software adoption, we've got the count. I'll call this CNS for the count of the new software. That's a num. That's this guy right here. Okay, and in this case, we have a company that purchased a new software program, and they want to see whether or not people are using it. It stands to reason, makes a lot of sense. So what they did was they collected a lot of different variables. I wonder if it varies by department. I wonder if it varies by shift. I wonder if it varies by if they were trained in the old software. I wonder if it varies by their support, by the level of support we provide them. I wonder if it varies by the amount of paper that we use. We want to see if there's a correlation between those two. All right, anyway, so there's lots of different variables, right? We're interested in, for this case, let's see if it varies by shift, which is a cat, right? You can see that that's a cat. Looks like evening and day. So let's take a look at that. Again, our PGA wheel, that's a one num, one cat, right? So our PGA wheel would say, hey, first look at the, here's, whoops, I've got to select the data, which I didn't do. Select the data. Notice I'm selecting all of it. Still going to do just one num, one cat. We'll go to count of new software, and now we'll look at it by shift. There it is. Okay, let's take a look. Here's our box plot. Let's click on that and see what we get. Here's a good case of something that doesn't look like the means are different. Do you see how the centers of these boxes are more or less the same? I know that line's a little bit lower than this line. That's actually a median line. But yeah, I know that line's a little bit lower than this line, but not a huge deal. Okay, I may not expect there to be a difference in means statistically between these two, even though if I go up to the data and description, they may not be exactly the same. Boy, they're pretty close. But that can often happen with data. You see data that, yeah, the means are different technically, but they're not very different. And if you think about it, the difference between these two is very small compared to, say, the standard deviation. So you need a lot of samples to really see that. That's my guess anyway. So if I were doing my PGA wheel, I may not even go to do the test, but let's go ahead and do the test anyway, just for completeness. So in this case, I'm going to look at the mean of my null hypothesis is going to be, I wonder if the mean of the day shift is equal to the mean of the evening shift. Versus, I'll just call them D and E, versus the alternative. They're different. Now, I have no preference whether they're greater or less than, right? I have no preference. Notice I'm not saying, hey, I looked at the data and one is greater, so I better test greater. It's important not to do that, not to have any sort of a priori looking at the data. No, you want to formulate your test based on not what you see in the data, but what your hypothesis is going in. Okay, that's an E. So let's take a look at it. The p-value is, drum roll, please, I can't do that with my head or with my mouth very well. Go to tests in two categories, and there it is, 0.85. Okay. All right, so mu1 and mu5, that's a not equal. 0.85, certainly greater than 0.05. And look at that confidence interval. So here's a good example of the confidence interval overlapping 0. Notice it goes from -5 to +4. So it crosses over that 0 point. All right, so let's go back to here. And I'm not going to write out a lot of these other ones, but let's just write in the p-value is equal to 0.85, which is greater than 0.05, so the null does not go in this case. Tactically, what we do is we say we're sticking with the null. Remember, innocent until proven guilty. We haven't really proven the null, but that's tactically what we're doing. We're going to say, okay, for purposes right now, it does not differ by shift, so we can't really say that this is true. Okay, that hypothesis is not really supported by the data. All right, and remember that also that the confidence interval went from, what was it, -5 to +4. And somewhere in there is 0. So that means that 0 may be an estimate for the difference between these two, which basically says there's no difference. If 0 is a decent estimate for it, there's probably not a difference. Okay, so that's the shift. I just want to show you how quickly you can do some of this stuff once you get used to it. And then we'll show you how to do that in I didn't show you how to do this in Minitab, so I'll show you how to do it in Minitab. What if we wanted to look at trained in old? Well, again, we could draw the box and all that stuff. I'm not going to do that right now, but again, that's one num, one cat. I believe I already have it open, but I'm going to select it anyway. Okay, count versus trained in old. Let's take a quick look. Here's the box plot. Wow, it looks like a difference. Let's see if it is. Yes, the p-value says that there is a difference. We can come over here and verify that with a confidence interval. Pretty slick, right? We can do that very, very quickly. We can look at lots of different things very, very quickly. All right, let me show you how to do that in Minitab. I mean, so far, all the stuff that we're looking at, Minitab is slower than Excel stats, but I think you'll see that there are some things where Minitab does very well, or that Minitab does very well. Let's do this, and let's do the trained in old, because, or let's do the shift one first, see if we get that p-value of 0.85. So in this case, we're doing a 2-sample T. My samples are in Count New Software, and my subscripts, Minitab calls categories subscripts, are stored in Shift. Okay. Yes, I'll do a box plot because I like that. Here's where my options of the test difference or alternative not equal. I'm going to leave those alone. Click OK. Yep, look at that. Doesn't look much different. You knew that was coming. And then there's my p-value. See that? 0.857. There's my confidence interval. So Minitab gives the same answer that Excel stats did. Okay, and because we are here, let's also, if we do a Control E, and Minitab Control E says, do it again, do it again. Click on trained and old. Now we can test it for trained and old, and there we get that picture. And there's our p-value. So it definitely is significant. And you'll probably recognize that from the Excel stats. Okay, so that's how to do it in Minitab. Stat, basic statistics, 2-sample T. All right. Now, one other thing, and this is a preview of what's coming. What happens if we have more than 2 categories? Like, for example, support had 5 categories. What do we do then? Well, the first thing is always to plot things. And here's why I want you to do the boxes. Look at this. This is a very complex picture. That's very hard to tell whether one group is different than another. If I look at separate frequency charts, that's better, but look, it puts them off the page, and I have to go back, and that kind of taxes my short-term memory for comparison. But box plots, do the trick very quickly, I can very quickly see, boy, this guy right here is hovering above the others, and it looks like these three are about at the same level, and it looks like this guy's a little bit lower. So I can tell that very, very quickly at a glance in a box plot, and then I can do the testing that I want to do. Okay? Just an idea, or just to give you an idea about all of this stuff. So let's wrap up that example. So again, the t-test, great for making comparisons of means. We're going to use the 1 sample and the 2 sample. Now, one thing I do want to point out is that a lot of people make a big deal about having to have normality in order to do a t-test. As we saw in the last lecture in the supplement, that the central limit theorem protects us a lot for that. In fact, t-tests are very robust to departures in normality. Only if you have very skewed data should you worry about it. If you have symmetric data, no problem. Almost always a good test to be using if you care about means. If you have extremely skewed data, then maybe you do a median test. We'll do one of those at the end of the lecture. But I just want to not caution you, but throw caution to the wind, if you will. Be a little bit more cavalier in that. You know, assumptions, you can easily get into the game of saying, you know, put all these qualifications on every bit of analysis that you do. So basically nothing is strictly speaking true. We all already know that the world is not simple mathematics and that we have to make models in order to make conclusions. That's all these tests really are. They're just giving you a much more deeper look into whether or not what you see in a plot is real. And that's really what we have to keep in mind. T-tests are very robust. All right. So that's that. Let's go ahead and what I want to do is I want to do the example that's now on 128, which is on gas mileages. Okay. So what we're going to do, oops, and I shut down Excel stats. I should not have done that. Okay, open it back up. There you are. Okay. So we're going to do the example of gas mileages. There we are, right there. And in this particular one, is that? There we go. All right. And in this particular example, what we've got is we've got a test track. On a test track, we took a specific car, and we had female and male drivers driving around on a test track, and we wanted to see if there were differences in mileages. It was a test track that included stopping and starting and some other things. We wanted to see if the gas mileages that different drivers had, if that mattered, if gender mattered. In other words, if you were a man or a woman, right? So again, that's a num, and that's a cat. Okay, so again, first thing that we ought to do, PGA, is make the box plot. So let's go ahead and do that. But I'm going to be very specific here. Let's do this one in Minitab. You'll see why in a moment. Here's one of these cases where Minitab actually certainly beats Excel stats. Get rid of that. Just a moment. Okay. So I got mileage and gender. Let's make a box plot. We haven't done box plots in Minitab, so here we go. So we'll do graph, box plot with groups. You'll see what the group is, mileage versus the group, gender. And let's take a look. Okay, so the first test, remember when I said something like, well, I have this test called the UFO test. And certainly there's a lot of hovering here. So UFO test says looks like means are different. But here also, when we do boxes, we're going to be looking at, every time we do boxes, we're going to be asking two questions. The first is, are the means different? The second is, are the standard deviations different? The way that you tell that one is not the UFO test, but what I call the birthday present. Okay, and in the birthday present test, you look at the size of the boxes themselves. Okay, so the extent, I'll just actually sort of highlight this guy right here. Okay, versus this guy. Oh, right here, my penmanship could be better. That's for sure. Anyway, those two boxes right there, and I asked the question, is one of these birthday presents bigger than the other? Okay, now don't worry about the ribbons that are on the package, right? We don't care about that. We just care about the size of the box. All right, now there's a saying in the box that goes like this. It says, good things come in blank packages. That blank should be small, right? Good things come in small packages. In most process situations, you would like to have, it's a good property to have the consistency good. Okay, that means a small variation. So that relates to the package. And so you can think about that. If you have a big package that has lots of variations, could be anything. If you have a small package, it's probably like a DVD or who knows what, right? It's probably not a book, maybe. Not that those things are bad. Those things are good. All right. So this is, getting back to reality here, this is really going to test whether sigmas are different. Okay? And that's what we're interested in here. Now, we already know that to test the means, we can do a two-sample t. So we can go ahead and do that. F3 is another one of those things that's helpful because it clears everything else. We want to know mileage by gender. And in fact, when we hit that, there's our p-value. Yes, it's significantly different, and here's the gas mileage that it differs by. Okay? But what I want to do is I want to really test that second one, which was based on the sizes of those boxes, which is a test of variances. So let's go ahead and do that in Minitab. Now, it turns out that well, let's just go ahead and do it in Minitab, and I'll show you how to do it, and then we'll have a couple of comments. So that's in Stat, Basic Statistics, Test of Two Variances. That's pretty cool. It's right there. We have our samples, and then we have our subscripts. See, it works just the same. Graphs, we want any graphs? Nah, not this time. Already have them. And here it is. It gives you, let's see, maybe I will do the graphs. Let's do the box plots. I like it because it puts it on. Oh, it didn't do that. It used to put it on there. Minitab got rid of some of its stuff. But in any event, here are the tests. And this is it, okay? So it gives a little bit of stuff here. It gives the gender and female-male ratio of standard deviations. Turns out that standard deviations is a ratio test, but we don't really need to know that. We just need to get that p-value. And there it is, but it gives us 2, which perplexes us. So in this case, so first of all, let's just be blunt here. The only time when it matters is when we get conflicting results from the p-values, right? One is less than 0.05, the other is greater than 0.05. In this case, they're both greater than, which seems to support the conclusion that there is no difference between the standard deviations. Now, it certainly looked like there was, but it turns out we don't have enough data. See, there's a good example of where our eye kind of deceives us. Our eye can kind of deceive us. If we look at that box plot again, let me go back to the plots and see if I can pull up there's our box plot. So that says whatever we saw here, like the difference in the size of the box, wasn't real. So when we ran our hypothesis test, sigma m is equal to sigma f versus the alternative sigma m is not equal to sigma f, we got a p-value greater than 0.05. Therefore, we fail to reject the null. And effectively, we say that the null is, we work as if the null is true, even though we haven't proven that to be the case. We act as if it's true. We don't have enough evidence to really support our theory that they're different. So we're going to keep going forward. So here, again, like I said, here's a good case where even though the boxes look like they are different in terms of how much variation they have, in terms of how big they are, there isn't enough data, at least, to support that conclusion that they really are different. So, getting back to this example, it certainly does look like, in this case, women get better gas mileage than men, but there isn't enough to support that conclusion when we talk about, are men more consistent than women in their driving. Again, I want to emphasize this is a specific car on a specific track. All right, before I get myself into too much trouble. So that's how all that works. Now, why did I bother going into Minitab? Well, the reason is, see if I can get back to the session window. There we are. The reason is they gave us two tests, F-test and Levene's. Why? It turns out that the F-test, unlike, remember I told you that the T-test is very robust when it comes to departures from normality. It turns out that the F-test is not. So if you want to do tests of variances, either if you're going to use the F-test, which is usually the choice of the test of choice by most people, you have to have normality. Otherwise, in Minitab you have the option of going to Levene's test. In Excel statistics, we don't even have that option. So there's not even a way to show how to do that. That's for a different lecture on a different day. But for now, we can do the F-test. Okay, so how do you test whether the data are normal? Well, again, you can look at, I like looking at plots. Let's take a look at a probability plot. Here we have multiple ones. We have mileage, and we want to look at it by gender and see if those give us normal data. And lo and behold, it looks like the women, right, female, the distribution for female drivers is normal. See, it's within these sort of confidence bounds. Normal is not a bad model to use there. But for men, sorry guys, it is not normal. See how that curve does not line up with that straight line? You can see it kind of goes way out. So I guess that just supports that we're not very normal drivers. All right, again, before I get myself into real trouble, let's move on this one. So in this case, the Levene's test number would have been preferred, but both would tell us the same thing anyway. All right, I'm not going to dwell too much on this other than to say in Excel stats, if we're doing mileage versus gender, the t-tests, no problem. Here's our summary again. There's our box plots. A little bit hard to read the box plots, so we'll change the scale. 25. Good enough. Certainly looks like a difference, and same sort of difference in the size of the box. Let's see if that's real. T-test says, yes, the means are different, just like we got before. Here's where you do the F-test. Notice there's no Levene's test, so you're stuck. The only thing you can do is the F-test, which we should check to see if the data are normal. Probably the best way is to simply look at the separate frequency charts and see whether they look normal. And you can see that, yeah, there's the distribution for the men. It certainly looks a little bit right skewed. Whereas the women, it doesn't look normal, but it looks symmetric, which is usually good enough for these things. So we probably wouldn't do an F-test, but just for giggles, let's see what we get. And there, lo and behold, remember we got 0.221 for the p-value. Excel stats gives you the same answer. Okay? So if we wanted to test it, we would still reject, or we'd still say the null is, yeah, the standard deviations are the same. Okay, so that's that. So that's variances. And remember, I mean, variances, they're an important test, but the test of variances is an important test, but not as important as the test of means. So let's move on. And what I'd like to do next is the test of proportions. And for this one, I'm going to use the example that we have on 134, which is CGI. So let me use CGI. Go to the CGI data. Okay, so in this case, let me draw the whole thing out. I know we're moving fast here, but you can use the back button or the stop button or whatever you like. Okay, let's diagram this out. So this happens to be, for example, from the gas company, although you'll see it's analogous to a lot of different things. When the gas company comes to your house and reads the meter or needs to get in to fix a gas line or something like that, they send a technician over. And if you're not home, they can't get into the house. And so that's a problem for them and for you too. So they wanted to measure something. They measure something called CGIs, which stands for can't get in. So that means sort of on any time that they send a driver out, they either get in or they don't. Now, if you look over here, that's what we have. We have a no or a yes. That's certainly a cat. Okay? And somebody had the hypothesis that, oh, well, maybe one fleet manager varied from another fleet manager. So we've got two of them. That's also a cat. So we have two cat here. Okay, so in this case, what we're going to do is be looking at the proportion of CGIs. That is the ratio of no's to yeses on CGIs if they differ by manager. Another cat, right? Test of two proportion. Okay, so again, the first thing is the PGA. We'll just go ahead and do that plot right here, and I think you'll see it. Here we'll do a bar chart, and we'll see if we get a difference. Let's do this in Excel Stats first, and then we'll do it in Minitab. Not one num, one cat. This time it's two cat. And by the way, the extension of the t-test to n categories is called ANOVA. The extension of the two proportion tests to multiple categories is called the chi-square. So we'll explore both of those in a later lecture. But for now, let's walk before we run. Okay, so here I've got CGI by manager. Let's take a look at the picture. Tables of data can tell us things, but boy, you really have to stare. Here's a nice little picture. I find it nice anyway. And sometimes Excel Stats has this really nice feature of being able to swap the variables. Sometimes the other way of looking at it is more revealing. Let's go ahead and click on that. But certainly it doesn't look like there's much difference in these proportions. In fact, yeah, there's maybe a little bit different, but not much. So one of the questions I might ask is the proportion of CGIs, that would be a yes, does it differ by manager? So let's write out that it certainly looks like it differs a little bit, but maybe that's not significant, maybe it is. Okay, so let's see if we can back that up one way or the other. Let's write out the hypothesis test. It looks, maybe, I'm not convinced, maybe a difference between CGIs. So I wonder if the proportion of CGIs differs by manager. So our null would be the proportion, I'll write it as pi. If pi of A is equal to pi B, right? Or the alternative is pi A is not equal to pi B. Notice how I don't have a preference for which manager, right? So that's how I'm writing it. Incidentally, just to be very, sort of explicit about this, I write it as HA is equal to HB, but I could have easily have written my null hypothesis as pi A minus pi B is equal to 0 versus not equal to 0, right? Alternative. Right? Those are equivalent statements. And if I solve this equation, right, if I move the pi B on the other side, I get pi A minus pi B is equal to 0. So these are two equivalent statements. I just wanted to point that out just in case you were wondering, because it does look a little different. Okay. Back to where we were, which was 2cat. So let's go ahead and do that test, and let's see what the p-value is. To do that in Excel Stats, it's on the test R by 2. R by C will get us to a chi-squared test. All right, let's check it out. There's our p-value. Notice it says 2 sample tests for differences between proportions. And there's our confidence interval. Notice the confidence interval overlaps 0. Already a tip-off that this is not significant. P of 0.35. Nope, it just is not significant. So we cannot reject. The null. So effectively we say we're going to go with innocent until proven guilty. We have to look elsewhere for improvements. We can't look at which managers' differences, or that the difference that we see in managers in that plot is not statistically significant. Okay. All right. Let's look at doing this in Minitab. Sorry, I spazzed out there for just a moment. Let's look at it in Minitab. Back to there's my project manager. There we go. Okay, I just want this guy. Okay, I'll get rid of the mileage versus gender. Don't need that anymore. All right, so that would be in stat, basic statistics, 2 proportions. And now I get a bunch of different options. And some of these are helpful because, I'll show you in just a moment. So in this case, we have samples and subscripts, and if we click OK, and we have the same options. Click OK. I think you'll see right away we get the same p-value. You see it's the same p-value that we had before. There's a same confidence interval that we got before. But I'm just going to summarize this for just a moment. I've got 20 out of 97 and 15 out of 97, right? See that right there? So B has 15 out of 97 chances. A has 20 out of 97 chances. I'm going to show you how to do this in Minitab. Sometimes you'll just have that summary data. That happens a lot with categorical variables, whereas I just have the summaries. I just want to put in the counts. If you do the 2 proportion test, I just want to show you how to do that. You can just type that right in. If we have 20 CGIs in 97 trials versus 15 CGIs in 97 trials, I just can type that in if I don't have the data itself, the raw data, whereas I can't do that in Excel Stats, which is kind of a bummer. Excel Stats needs the raw data for this to work. And you'll notice that you get the same answer in Minitab when you type it in as when you type in the summarizing instead of simply having the raw data. Okay, I just wanted to show you that. All right, let's do one more example because proportions are pretty important. For this example, we're going to use, I'm going to shut this down and Excel Stats as well. Shut this down. Okay, we're going to use the example of tax abatement, and I want to show you that this is something that you can do that there's a couple of different ways to skin a cat on this one. So in this, now this is more example than we just did, but in this example, we're interested in, this was a marketing group that went and a city wanted to provide a tax break, wanted to allow a company to erect a cell phone tower, and they were wondering if in order to do this, they would give a tax abatement to the people who lived in here, and they wanted to see if the responses that they got, they administered a survey, and that was one: would you agree to the tax abatement? Would you disagree with it, or are you neutral? So there were 3 answers. What they cared about was the agree, the percentage of agrees. We'll say percent agrees. Okay, now again, right now, well, I'm not going to say percent. That was wrong of me. It's just the whether you agree or not. Notice that's what the data are. That's a cat. Now, what we wanted to see was whether it varied by whether you were in the city or whether it was rural. So we'll just say demographic, and this is city versus rural versus country, city versus country, right? That's also a cat. All right. Well, in Excel stats, I won't go through the whole thing here, but essentially what we're looking at is the null of, we're going to look at the null of whether my proportion of agrees for the city is equal to the proportion for rural versus they're not equal, right? That's my alternative. By the way, this ought to be getting boring, just writing this statistical test. It ought to be becoming second nature. It's always equal, not equal, equal, not equal. The hard thing to write is, which symbol do I put in there? Proportions, you write pi. Means, you put mu. Standard deviations, you put sigma. All right, fairly straightforward. Let us, as the rabbit said, move on. All right, so let's go ahead and do this in Excel stats, and I think you'll see, there's my 2 cat, that we're sort of back to what they do well. All right, rural versus city, let's swap the variables. Yeah, it looks like this is what we wanted. Boy, it sure looks like the proportions are different in the city versus the country. But again, what if we didn't have all that much data? How much data do we have? We only ask 100 folks. Is that really enough? Let's see if it is. Let's see if it's statistically significant. Okay, so when I click on test R by 2, luckily, Excel stats has all the categories of our response. So if we wanted to test if we cared about agree versus disagree, if we cared about disagree versus by rural versus city, we could choose that. Or if we cared about the people that are neutral, that's different. The proportion of neutrals in the rural versus city. Here we care about the agrees, so we're going to click on that. Look at that. No question about that. The p-value is low, so the null must go, and we reject the null in this case and conclude that it's different for the folks in the city versus the folks in the country. Okay? Now, if you wanted to do that in Minitab, so far so good, right? Maybe not, but hopefully. So we would reject the null in favor of the alternative. Yes, there's a difference between city and country folks when it comes to getting them to agree to this tax abatement. So it tells me maybe where I need to focus my efforts or my campaigns or change my messaging or whatever. Okay? I don't have to put guesswork into it. I know that it's true because I've checked to see whether it's statistically significant. Okay, hopefully that makes a lot of sense. Now, what would happen if we wanted to do this in Minitab? Well, if we wanted to do it in Minitab, the problem is that the response isn't binary. It's not just yeses or nos. So I need to know sort of how many agrees and how many disagrees and all that, and out of how many. Yeah. So there's a number of different ways I can do this. I can tabulate it in Minitab. I can do that, but it does make it a little bit more difficult to do. Let's just see if we can do that in here. If you are using Excel and you have Excel stats, I'm going to use Excel stats to do this because I think it's fairly straightforward. If we do 2cat, it does kind of give you the numbers right here. So it says that and I'm just going to write these down. It looks like agrees in rural were 17 out of 37, and in the city it was 6 out of 46. Now you could have gotten this if you know how to use pivot tables. You can do that sort of thing as well, and that's instructive. In this case, there aren't that many data points, so you could actually count. You could count the number of agrees. You could also, if you're, just to be very, very explicit here, we could also use an if-then statements, and then we'll just call this agree, question mark, and do an if-then on that one, equal if this first column is equal to, quote, agree, comma 1, comma 0. Put a 1 if it's agree, put a 0 otherwise, and you can see for the agrees it'll be a 1, for everything else it'll be a 0. See that? See that? Okay, and then we can count the agrees, and we want to do it by city and by rural. That would be kind of painful, and it'd take a while. Okay? Or, if we just did this, we could port it directly into Minitab, and the whole thing would work. Instead, what I'm going to do is I'm just going to go to Minitab and enter in those numbers that we got. Basic statistics, 2 proportions, clear out the data, and use summarized data. So remember, in rural, it was 37 trials. 17 said agree. In the city, it was 46 trials. 6 said agree. Let's see if that's the same or different. Bam, 0.001. It's different. There's our confidence interval for the difference. A Minitab can do it. You just have to work a little bit beforehand to summarize it. Okay, it's much easier in Excel stats. All right, let's move on to the last one. So that was the 2 proportions test. And again, it can help you when you have categorical data. You're looking at things by responses by another category. So, for example, you may want to see if people prefer Pepsi over Coke, and you may want to break that up by gender. I wonder if it's different from males and females, or by blue color versus eye color. Don't know why, but it could be. Or by whether you liked old Coke versus whether you didn't. Okay. Let's do this last example. So we've actually covered a lot of the things so far. We've actually covered means, standard deviations, and proportions. And keep in mind that means and standard deviations kind of go together, because here we have the 1 num, 1 cat situation. And proportions, it's 2 cat. All right, let's do the last one, which is medians. Again, I want to emphasize that this is rare that you use this. It's only if you have typically very skewed distributions for all of your categories of your response. Okay, for this, we're going to do the procurement example as given on slides starting on 139. So here we've got the time that it takes to procure an invoice. You know what? Let me draw this up again. I know you're getting bored of me drawing the box, but it really does help to kind of understand the context. Obviously in your project you won't have to do it all the time because you already understand the context, but I still tend to do this. Procurement time. You would probably just call it cycle time if you were in your process, and that's a num. And in this case, I'm looking at department, and that is a cat. Looks like it's department A or B. Again, if we have 3 departments, then we're talking about ANOVA. That's a different lecture. All right, same sort of thing. Let's 1 num, 1 cat this. See what we get. Okay. So here is our box plot, and blah. Well, it doesn't really tell us that much. Now here's a tip-off. When you're looking at a box plot like this and you don't see anything on one side, that probably means it's very skewed data. And just to give you an idea, if you look at this histogram, you bet it is. If you look at the separate frequency charts, same thing. You bet it's skewed data. I'm going to make these histograms instead of frequency charts. maybe change the number of classes. Go from 0 to 1600. Yeah, this is skewed data, and it's pretty darn skewed. So there's a couple of different things. One of the things you could do is transform the data. You would probably want to do a log transformation on the data. We're going to cover that next week, mostly in the context of regression. But here's a good case where taking a log transformation of the data may help you a little bit, give you a little more insight. But without doing that, let's go ahead and use the test. Here's just a good test to say, well, you know, the data really are not normal. I don't feel totally comfortable using a t-test with that. I'm going to do a test on medians. So that's what we're going to do. If we look at here's the means. That would be the test on means. It looks like there's no real difference. If we go over here and see that the means test, there's the two sample t. It's not showing us anything, but I wonder if the median test would be. Now in Excel stats, the Mann-Whitney test is the one that it does the test for differences between medians. Let's write this out so that we see what the hypothesis test would look like. Again, this ought to be getting really boring at this point. My null would be, I wonder if nu A is equal to nu B versus my alternative nu A is, you guessed it, not equal to nu B. All right, we're going to run our hypothesis test and see if they're the same versus they're different. And voila, p-value of 0.357, which I hope you know by now means that p is greater than 0.05, which means we do not reject that null. And we effectively say, can't tell the difference between departments if we're looking at procurement time. We've got to find other things that make a difference if we want to find something where we can make an improvement. Okay, we don't have any statistical evidence that they're really different in terms of the median. Now, we also did test that average now, didn't we? By looking at that t-test. That really is a test of the average, and t-tests are fairly robust. Again, if you really wanted to do it, you'd probably take a transformation of the data, but to me this doesn't seem worth it at the moment. So let's just move on. Okay? Let me show you how to do that in Minitab. In Minitab, it's a slightly different test. We're going to be doing the Kruskal-Wallis like it is outlined in the book, which is outlined in the book. Oh, yes, I do actually have to go into Minitab to do this. Now, here's the hardest part about doing this. It's not in stat basic statistics. It's in stat non-parametrics. Now, why is it there? Well, it just happens to turn out that a lot of tests on things like the 50th percentile, the median, remember the median is the 50th percentile, or the 75th percentile, or tests on percentiles tend to have to be done, and when you want them to do on something, they involve something called order statistics, and ways to test those are what are called non-parametrics. The good thing about non-parametric statistics is, without getting into it, is very few assumptions. So, for example, there's no assumption of normality at all in this, or any other distribution. There's some assumptions that are, again, very, very robust, like I have something that's okay to model as continuous, which we have pretty numeric data here. Some cases you need them to be symmetric, but for the most part, they're almost assumption-free. That's the good thing. The bad news is they're simply not very powerful, so it takes a lot of data to really see differences. And in fact, you will find that with the median tests, that often there will be pretty big differences, and the test says, no, there's nothing significant here. You may need more data. In such cases, it may make sense to transform the data and do a t-test. Okay, let's take a look at the Kruskal-Wallis. A lot of people like to use a Moods median. I like Kruskal-Wallis. That's what I learned. Either one is fine. Okay, so procurement time is our response. Our factor is department. Let it rip. There it is right there. There's our p-value, 0.358, which again leads us to the same place that we had before. That p is not low, so we do not reject the null. And here is what we got right there. 358 looks kind of similar. So Minitab, Excel stats give the same answer. So if we go back to our thing, we do not reject the null. And that's that. Okay. So we've gone through a number of examples. Let me summarize it. Let me take a moment to summarize. We've covered means, and remember that for means the symbol is mu. We'll be doing t-tests. We did a 1 sample and we did a 2 sample t-test. We did a bunch of those. That's the most important one. Get that one down. We also did tests of standard deviations, the f-test and Levene's test. F-test works for distributions that are normal. Levene's test works always, or almost always, so it's much more robust. Okay? Remember, the t-test is very robust to departures from normality, but the f-test is not. That's the only thing that you have to worry a little bit when you're doing f-tests. It tends to be conservative anyway, so it'll fail to reject when you actually do have evidence to reject. So that's not as serious as convicting somebody, on the evidence that's not right. In other words, saying that there really is something when there isn't. We covered the 2 proportions test. Remember that was it was called two proportions, and it was testing the pi's. And finally, we tested medians. Not, in my opinion, one of the more important tests, but we've done it, and now you know how to do it, which is good. Kruskal-Wallis and Minitab, Mann-Whitney, and Excel stats. Okay, keep in mind that that always when we write our hypothesis test out, that it's going to look like this. We have a null where we look at equality. Let me write it this way. Versus they are not equal. Okay? That's the key concept. And what we're simply saying is, do we have enough evidence to reject the null? Our theories are usually here. This is usually our theory. I think that there's a difference. Let's make sure it's not just the sample. If p is low, if p is less than 0.05, then we reject the null in favor of the alternative. Okay? Another piece of evidence is with the confidence interval, and these go hand in hand. We'll look for, is 0 contained in that confidence interval from A to B, or is it not contained? Right? Is it somewhere, say, over here? Is 0 somewhere over there? Which means that they have to have the same side. If you see the sign changing from A to B, negative to positive, that means there's no difference. If you don't see the sign changing, there is a difference. All right? Well, I hope you enjoyed this lecture, and I hope this helps a lot because we've covered a lot. We've covered a major section of hypothesis testing. Next lecture we'll cover ANOVA and extend some of those hypothesis tests that we do have. Thanks for listening.